Okay, so I can start. Yes. Yes. So no, this is the last lecture, and no, all lecture were around the idea of screening and relationship of this screening with W-algebra construction, integrable system, and so on. And I want to spend some time to just to repeat and maybe formulate in a little bit different manner the idea which is here. So first, the idea from mathematical point of view seems rather natural and standard, and does what? That we start with some category, and some abelian category we start with, and what I explained in my first lecture, this category may be category of representation of just universal enveloping of some semi-simple Lie algebra, but in later discussion it may be category of representation of vertex operator algebra in a simple case of Heisenberg algebra, and in a latest case this category of representation actually of some subalgebras or some algebra of skew polynomials of special kind. Anyway, it is some kind of category, and from this category we can, in principle, we can try to construct big category, and no, bigger category, it means what? That how much we achieve, it is some question, but first we want to consider some category with just same objects, but morphisms, we change them. We want bigger space of morphisms in this category, and we describe it by the following way, that we did it, it is some general scheme, but in my first, maybe second lecture, it was following, that if construction was what? In this case, I take represent G, universal enveloping, and adjoint representation. And from this adjoint representation, I produce some bimodal. Yes, and the construction was, this bimodal was following, that suppose we take this adjoint representation G, and suppose we take some Fermat representation of G. And suppose also that we have a vertex operator of such kind. Yes, then G is some subspace here, all space of endomorphisms give us bimodal definitely, and so I can consider free submodel like UG times UG, and no, it is surely too big, but at least we have evident map from this to this. where this G goes to space of vertex operator if we fix something. And we can product it to G from the left and from the right. Now, first of all, here we have, in this map, we have big canal. So some big submodel is going on to 0, and here we have evident part, because it is a vertex operator. It means that if I have M from G, and if I have some also X from G, so if I take M times X minus X times M, this is, so it is action from this side, this is action from that side, and this is the same as action of X on M. This is on the representation, so it gives us an evident kernel. But we have a little bit more, because here this G is acting in Fermat representation. And in universal enveloping of G, we have center, but because of some reason for us, Casimir is enough. And center and Casimir as a special element of a center acting on this representation by center, by some number. It means that if I take additional to this relation is following, that delta times X an M element from generator, so it means I have like this M times delta minus delta times M is 0. Now it is some extra relation, and it is very clear why, because I can write down delta is quadratic expression and using the first relation. After that, it gives me some evident quadratic relation that I act to M by some E from the left, some other generator from the right, and it is 0. Yes, and using this, I can determine by model Bg, which is not actually this, but it is, maybe it is bigger than submodel is generated, but I just determine this bimodal as a free bimodal generated by G, factorizing by the consequence of this. Yes, and after that, what we are doing. Next, we choose the element here. So here we have a space of generators G, which is embedded to this, and let us choose some element A from G. And this element A I call screening. Then suppose after that that I want to operate with this bimodal. I can, in principle, I can forget all this construction, how I get it. But it is this. And if I take two objects, say M1 and M2, suppose they are 2G models, so they are objects of category of representation of my algebra, then I just, no, if I have M1 and M2, that we surely have space of G gamomorphism M1 and M2, and this is morphism in our category of representation, and I want to extend this space. I want to add some additional map from M1 to M2, and they will be new homomorphism in some category. And this is doing with the help of this A. So what I have to do? I have to consider any map from Bg to this home, not to this, but home C to M1, M2, and this is bimodal. Yes, and if I have this, I can take, I can fix any homomorphism of such sort, and because I have A here, then it gives me some image of A. So A is here, so it's here also, and so it gives me some linear map from M1 to M2. And I want this map to be homomorphism in some big category. Yes, and so, well, after that, what's the question? That in principle, the question is that I want to take first composition of such morphisms, and after that asking about how extend category, if it's possible to be abelian and so on. Now about composition, it is what? That image of A is homomorphism. But suppose I have following things. Suppose I have M1, M2, and such kind of A. So I have such embedding and so on. And I have M2, M3, and I also have such embedding, some other embedding from M2 times M3. And I want to say something about their product. What is this? No, it is clear what is going on, that we have in this space of homomorphism some Bg, and we have in this space of homomorphisms also some Bg. So it means that we have a map from Bg times Bg to this home C, M1 to M3. Yes, but we are interested in what? We are interested in, we have element A here, and we have element A here. The composition is something which is good to denote by A square. These are some operators acting from this to this. Yes, and if we have such morphism from this to this, how to characterize it? Now, it is possible that morphism will be what? If we have such A square, then I can look on this side what is going on. So I have Bg times Bg, and here I have element A times A, and I can consider here the bimodal which is generated by this. And my first bimodal will be B, I denote it by B1, and this second, maybe it will be 2. It is some submodel here which generated by this. And actually, the second bimodal surely belongs to symmetric power, because A times A symmetric with respect to permutation. And then I want to say that according to logic of what I'm saying, that I want to claim that such kind of object also will be a homomorphism in my categories. So it means the following. I have representation B2 with a fixed element A square. And now if I have two representation M1 and M3, and I want to take map B2 to home C M1 and M3, and in principle any, not necessary constructing by this way. And here I have distinguished element A square, and the image of this element will be the also homomorphism in my category. Yes, and in principle I can extend it to B3, B4, and so on, and just saying that such kind of elements are homomorphism in my category, bigger one. And then now what is happening? Now, in principle, such construction looks strange because we can get some category by such way, but in principle, spaces of homomorphism is too big and rather hard to control. But nevertheless, what is screening business is doing, it is this, because in the I say a few words how this things is working in other situation, but again, mathematically situation is following. So we have some category, abelian category for any object M1 and M2. We want in the space home C M1 and M2, we have to find to distinguish some subspace and call it space of homomorphism in some big category. Big or small, I do not know what. And in principle, such kind of story can appear by the following way. If M a representation of some algebra B, yes, and if in B we have some subalgebra A, then the idea of extension is what? That we have morphism in category of B models, but we can consider M1 and M2 as A models. And in this case, the space of homomorphism surely will be bigger. Or we can determine A opposite if we can say how much the space of homomorphism become bigger, then we can find out, try to ask, is it some algebra A such that this new homomorphism are homomorphism with respect to restriction to this A. And actually this idea for W-algebra is going on, that in the case what I started with, or the case when I have G and element here and what I called the shift of argument methods, what is this? Then in this case, I have category of representation of UG, and in M1 and M2, they can be Verma, and some other representation, I have G and some element A here. Yes, and actually, I need not arbitrary vertex operator, but such that the corresponding bimodal B is coincide with bimodal which I described there. And I said that if we are talking about such kind of homomorphism from m to m that I explained what is this. Because we know how many vertex operator we have, and in such vertex operator I take A, and they will be homomorphism in this new category. So again, usually m chi is irreducible representation, and so space of homomorphism just constant. But now we have more than that. I can add, which is constructed by this way, or I can take what I denote B2 and then taking element A square from this, and or suppose this B2 acting from this to this, so I have more than that, and so on. And so have I such a big family of homomorphism from this to this. And in this case, it is, no, in some sense, because this situation is simple, that it means that I have such kind of Fermat representation, and I managed to construct many, many maps from this, and from B1, B2, B3, and so on. And so such space of homomorphism, it occurs that it is commutative algebra, which is acting in this Fermat representation, and this is actually the construction of my integrable system. Or I can say it a little bit differently. If I take m chi1 and m chi2 and they're different, then, and if I'm looking from B1 to this kind of endomorphism, then not vertex operator exists if chi2 minus chi1 is a root. But if for B we have some extra condition which arise from Casimir. And so it means that such kind of map exists, but for existence we need some condition for chi. So the situation is very close to what we have in any Virasoro type story. I construct something which pretends to be intertwiner of some algebra, and these intertwiners exist, they intertwiners between Fermat, but this Fermat cannot be arbitrary. Yes, and this is story here. And what is going on in a case when we consider vertex operator for Heisenberg? And how was it? I take category, what we start with, is a representation category of Heisenberg. In this case, suppose for simplicity, it is one component Heisenberg, HI, with standard relation. In this case, this category of representation, or what we usually saying that this category of representation, usually defined as semi-simple and irreducible representation of Fock representation of this Heisenberg, and P is momentum. Yes, and now we want, as following this idea, to extend the morphisms. So before extension, we have P1 and P2. They are irreducible, no morphism if P1 isn't equal P2. But we want more, and for that we take a representation which I denote, I think, maybe R alpha today with the basis Fi, and Hi Fg is maybe alpha I plus J, and we have the embedding of such R alpha to this. Yes, and but if it is vertex operator acting from fork to fork, then it is no, in principle I want to do the same. I want to take R alpha as subspace here and act in a sense universal enveloping of Heisenberg, and produce such kind of bimodal. And there are also two kinds of relations. One relation just from this, so Hi bracket with Fj is, so it is from the right, it is from the left, and it is kappa, not kappa, but alpha F I plus J. But it is also something like bracket with Casimir. And in this case, we can do what? We can write down Virasoro algebra by standard formula. H alpha, H beta, alpha plus beta equal I, like this. Yes, and this is quadratic expression. Yes, and if you take this Li, like operator acting from this to this, and bracket of this Li with Fg is equal to, it is also Fi plus J, and here we have some expression depending in alpha. I do not want to write down it precisely, it is not important right now, but here it is some coefficient which is linearly depending in I and J. Yes, so again, this is some analog of Casimir, and in our previous life it just commute with the element from G. And now it is similar but not the same, and it is some relation like that. And then up to some details which we have not time to discuss, but details mainly about what coefficient we have here. Then we have this this bimodal, and then we factorize it by consequence of this, surely, and consequence of this. And so we have some bimodal after that, depending in alpha. Yes, and then what is going on? If this condition is, no, I want to extend the space of gamomorphism, and we have Fp1 and Fp2, and I want to have a space of gamomorphism from this to this, but first of all, it has to be vertex operator. In my notation it was like this, and in order to have it, I need surely P2 minus P1 equal alpha. Yes, and also but and this is enough if we want only this condition. If we want conditions which follow from relation with Li, then it quantize P. So it means that such kind of homomorphism exists if P1 satisfies some condition and which condition you can find in any textbook about Virasoro algebra, and it means that actually it means that we can no we determine the extra homomorphism in a category and subalgebra which commute with that extra homomorphism with Virasoro, and by this way we trying to construct the representation of Virasoro algebra, and Virasoro algebra first, and then just one more thing, that we have this and by model, and it was by one in my previous notation. Then I can take B2, then I take B3, and so on. As element A, here I take F0, here I take F0 square, here I take F0 cube, and so on. And all of them give me my homomorphism in this bigger category. Yes. So I have category where objects still the same, but more homomorphisms. Then in principle, after that, I need to try to construct bigger category, and it means that if possible, to add kernels, co-kernels, extensions, and so on, and so it gives us category of Virasoro business. Yes. No, this is good to explain maybe in details, at least in some example till the end. But I want to explain, and I need to explain, how it is working in more complicated case, where we take what? We still have the same Heisenberg, Hi, still they have same category of representation, Fp, and then we take alpha and minus alpha, and we take this representation R alpha and R minus alpha, and they give us vertex operator which are acting this from Fp to Fp plus alpha, and this is acting from Fp to Fp minus alpha. Yes, and no difference now is following that if we are taking only one of them, I extend category using this. But if I play with two of them, I have more morphisms. So it means that for example, how it is going, that I have F0, it is Fock space, and I have F alpha, and I have F minus alpha. Yes, and before there was just irreducible representation of Heisenberg, but now here I have new morphism, which constructed by this way. And this new morphism is acting from this space to this space, and this is, if you write down explicitly what does it mean, so here we have this vertex operator, and I explained yesterday that this is Fock space, this is Fock space, and I can put it on a level 1, and operator F0 acting from this to 0, from this to this, from this to this, and so on. And this is morphism, new morphism in this category. And this is vertex operator corresponding to alpha, it is maybe 1. And from this side, we have vertex operator which is acting to this. And it is also vertex operator which is corresponding to 2. Yes, so in this case, if I want to apply this ideology, so how? So I have bimodal with respect to Heisenberg, which is something like B1, and if I acting this twice, it was B2, B3, and so on. And so if I acting by them twice, like this and like this, like this and like this, so it is product of F0, 1 times product of F0, 2. And no, again, it means that I have tensor product of 2 bimodals. I have here element F0, 1, here times element F0, 2, and I generate bimodal by this. So again, skip details. It means that for any numbers m and n, in this case, I can construct some bimodal Bmn, and morphism in my bigger category is just map from this bimodal to homomorphisms of space of homomorphism of Fock space to itself. Yes, and no, the interesting element of this story is that, no, first of all, maybe a few words about this. So you have homomorphism in this category, but because they are expressed in terms of vertex operators, then even such kind of morphism you can understand as a sort of composition. Yes, and if you now just statement which maybe I explain a little bit later, but now just statement. So if you have fp1 and fp2, and you want to calculate the space of homomorphisms in this sense, the space of homomorphism can be understood or can be identified with the space of homology of some local system. And let me just say what local system is here. So suppose we have fp1 and fp2. And suppose in my language it is bmn, which defines similarly, and just homomorphism here. And then I take a special element here, and so here I get some subspace of in space of linear maps from this to this. And this linear space can be identified with something. First of all, it depending in n and m. Yes, then we have to do the following. We have to take CP1 and make up the following thing, that we have to produce, first consider CP1 times CP1 times CP1 n times CP1 times CP1 times CP1 m times. Let us choose here coordinates, maybe y1 and so on, yn, z1 and so on, zm, and let us just write down the corresponding multivalued function. It will be the product of yi minus yj power alpha square times the product of zi minus zj power alpha square times the product of yi minus zj minus alpha square. Then we have a little bit more. We have the product of xi power p. No, let p1 times alpha times the product of yi product is how many of them we have. So here products I running from this, and it is not x, but it is yi, product of yi times p1 times alpha, and product xg times maybe here p1 minus p2 power alpha, and here product p1 minus p2 times minus alpha, and here z. Yes, I think this is correct, and it means that such kind of function it determines what? Now, first of all, this function we need to consider symmetric n-symmetric power of this and n-symmetric power of this. So what we have? We have C star, maybe it is CP1 without 0 and infinity, and we have symmetric m-symmetric power of C star here, n-symmetric power, times m-symmetric power of C star here. And this function which I wrote, it has singularity around discriminant divisors. So I have to delete from this divisor, so it is actually this is set of y that are all distinct. And here also, yes, and no, because we have y minus z, it means that better to write it that such product minus divisor. So we want all points to be distinct. Now what? On this manifold, we have a local system, one-dimensional. And structure of this local system in correspondence with this function. Now, local system, it means what? It means that we have a line and we have points of type y and points of type z. Yes, and also we have points of type 0, not point, just 0 and just infinity. And what is writing here? If we have two types of y, y1 and y2, if y1 go around y2, then we have alpha square as y-ending number. If one z go around other z, we have such kind of things there. If z going around y, we have this. And about this, maybe I write down this with some mistake, maybe not, I think not, but it means that if y goes around this, then the corresponding y-ending number have to be y power p1 alpha. And if it is going around infinity, it has to be minus p2 alpha. And similar with different sign with x. So anyway, it is the standard way to describe what is going on here. So local system I described more or less, but the statement following. We have local system, so we have this corresponding configuration space of points, and we have one-dimensional character of fundamental group, and then we can calculate the homology of this local system. And this vector space of this homology of this local system and the space of homomorphisms between corresponding Fock space, which I'm trying to describe by different manner, this is just the same things. Yes, and from the local system business, this is some kind of way to calculate how many of them, what is dimension of this local system, of cohomology of the local system. And even it is possible to formulate the composition of such morphisms, such if we have such classes, if we have something acting from FP1 to FP2 and from FP2 to FP3. And now, relations with quantum what is going on here? No, in some sense, we need to have in mind that these two screenings, as people usually think, they're generators of quantum group, and this quantum group is a affine quantum group, and for SL2 in this case. And Cartan matrix for SL2, here it is what? That in our construction, we have two vertex operators, and they give some momentum. And scalar momentum of this with itself is alpha square, with this is also alpha square, and between of them minus alpha square. So metric of scalar product is alpha square, minus alpha square, minus alpha square. Yes, and here up to a constant we can see the matrix is q square, q minus 2, and q minus 2, and 2, 2 minus 2 minus 2 is Cartan matrix for SL2 hat. Yes, and one more thing, that I describe also the maybe let me look to this picture. No, I wanted, and I still want to describe this idea, what is going on from the point of view of lattice and screenings, what I have there. But let me consider the very nice picture which actually we can see here. So what is going on? We have Fock space, and we have F alpha and we have F0 acting from this to this. And as I claim, this is Fock space, we can determine the action of Virasoro algebra such that this map will be intertwiner for this Virasoro algebra. Then we have F minus alpha. And here, component of vertex operator, which is acting here, F2. And this is intertwiner with respect to also Virasoro algebra. And these Virasoro algebras are acting here and here. And this operator intertwiner with respect to some other Virasoro. And these Virasoras are, they are related by some reflections. So structure of Virasoro is following. Li is the sum of H alpha, H beta, alpha plus beta equal E plus some I times some mu Hi. And so we have this alpha, and we can determine this mu such that such kind of expression compute with this F0. And this mu is actually alpha plus something. And then one Virasoro, this mu alpha times something. In alpha, I forget to write down precise statement, precise formula for this mu. But for one Virasoro we have plus mu. For other Virasoro we have other minus mu. And so there are two different Virasoro which are acting in this space. One commute with this, and one commute with this. But what is going on after that? We have here F minus 2 alpha, and here we have F 2 alpha. Yes, and it is possible to show that, so F0 is homomorphism in my new category. But it is also some homomorphism which is acting from this to this. And it is intertwiner with respect to corresponding Virasoro. And we have also homomorphism which is acting from this to this. Yes, and also we have such amount of homomorphism which are acting by which way? That we have this 0 alpha, 2 alpha, 3 alpha, and so on, minus alpha, minus 2 alpha, minus 3 alpha, and so on. And so first screening is homomorphism from this to this. Then we also have homomorphism from this to this. We have homomorphism from this to this. All things which are symmetric with respect to this. And again, the intertwiner or screenings and so on, they exist at least in such case. And if we take second mirror like this, we can use this. And then homomorphism are acting from this to this, from this to this, from this to this, and so on. Again, structure looks rather nice. So we have no, what is going on here? It is possible to formulate even without any mentioning of these complicated things about category, local system, and things like that. We just have the sum of this f m alpha. We have two Virasores, Li first and Li second, and they are acting in this direct sum. And we on this direct sum, we have a homomorphism with respect to of one Virasore or with respect to another Virasore. And they are morphism in the some category which we want to determine. And the idea is that in principle it is possible. We can determine some space of morphism which such that such homomorphism with respect to these two Virasores are homomorphism in this category. Actually, it is not very easy to explain, but the situation actually is much more interesting. That we on this space we have a family of Virasore algebras which is acting there, and we can consider the homomorphism with respect of them. It is also will be a part of homomorphism of this bigger category which I want to construct. Well, and now no, again, this category is deeply related with category of representation of UQ SL2 hat, but actually I said that in UQ SL2 hat, the parameter Q is exponent pi I alpha square, and we also have level. In principle, any level involved in this situation. Right now, let me consider the case when k equals 0 only. Then what we know? Suppose alpha square will be generic, and before going to quantum group, in principle, I can consider case q equal 1. And structure of category for generic q and for q equal 1, where it is usual SL2 hat, is the same. Yes, and now let VH will be Fermat representation for SL2 hat no, k is 0 and h is highest weight. Now SL2 hat is, it has basis SL2, no, basis SL2 times I, and in SL2 we have E, H, and F. Anyway, this, no, this H is because of this H, but let us use some other number, say beta here. Yes, and the H acting on the highest weight vector is beta times V. Now, what is, suppose beta is 0. Then what is the structure of this representation? So in this representation, this is Verma representation for so beta is 0. It is surely very special case, and k is 0. It means that such representation has one-dimensional representation as a quotient. And such representation, it has many, many singular vectors, and such singular vectors are arranged by the following way. We have highest weight vector, and let me use also some notation. E0 will be E times 1, it is from SL2, and E1 will be F times T. And E0 and E1, this is two generators which give us nilpotent subalgebra for SL2 hat, and let them be creation operators. Then in this special case, we have the following singular vectors here. I can act by E0 and then by E1, and because quotient is one-dimensional, they are singular vectors. But after that, we have more. I can take this and act by 3 times, and it will be next one. And then I can act by 3 times here, then 5 times here. So singular vectors, they have the following top vector 1, singular vector, then E0 times 1, then E0 times 1, E1 cube, then 1 E0, E1 cube, E0 5, and so on, and symmetrically 1, and we have E1 times 1, and we have E1 E0 cube times 1, and so on. And so they are organized by such structure, like this, and so on. And what is the relationship with our picture here? Then but before explaining this, let me just say that I said that this is common knowledge in a case when Q equal 1, but no difference in quantum case. It is just the same formulas and so on. And maybe interesting story is that they are singular vectors, but the structure of submodel is following. It is big one, then we have these two, which are generated by this, and intersection of this submodel, which are generated by this two, is generated by these two. It is like this. And algebraically, it means some kind of some identities. So it means that if you write down like this, so E1 E0 cube, it can be rewritten as E0 times something. So these belong to representation which generate by this. And no, in this case, it follows immediately from Serre relation, because it is, if you write down a Q commutator, for example, it will be several terms, but one of them will be this. In all other terms, E0 will be there. So you can write down it like this. And so for this and this, it is just Serre relations. And if you're going deeper, that is more complicated identities, but logically it is some kind of relations like this. And anyway, what is relation with this story? That relation of this story is following, that we have two screenings which are like this and like this. And we have not something like functor, but now it will not be functor, but some correspondence. This correspondence take f and alpha, and it gives me the Fermat representation for such UQ SL2 hat with the highest weight. Actually, it is n. No, it depends on convention, how we, in quantum group, no, if a group is not quantum, it is just n. But in quantum case, we have to write down something q power n. But anyway, it's something like this. Yes, and it is such kind of correspondence between two quantum groups. Yes, and then I want to say the following, that if I take Fn alpha and Fm alpha and want to determine home between them in this extended category, which I tried to describe before, then this space is isomorphic to the space of home of corresponding Fermat to corresponding Fermat in SL2 hat, in the quantum SL2 hat part of a story. Yes, for example, maybe I, no, let me say it no, you can criticize this notation because they are slightly non-standard. But what is going on? That I have this, and it is Fermat representation with highest weight 0. Yes, and after that, inside this, we have, if it is Fermat, we have embedding of Fermat, which is corresponding to this vector. It is V1, and it is V minus 1 in my notations. Because no, from this at least it is clear what I have in mind and what is the meaning of this one. But standard highest weight, we use slightly different things. And other things that, in my case, homomorphism is going in this direction. In Fermat representation, it is going in opposite direction. So we need to consider such homomorphism and reverse this. It is, after that, such kind of correspondence will work. Anyway, now, what is going on in this correspondence? So here we have Fermat represent. Again, what is corresponding with what? We have Fermat representations here. It will be V0 and all Fermat which are sub-representation in them. And the corresponding vectors I write here, they're here. And how it is going on. So this highest weight going on to this, and this highest weight, it is going on to this, and so on. Yes. And no, at least I think, no, it is definitely correct and clear what I have in mind. And about the standard way to label Fermat representation, you can forget, but it is easily can be fixed. But we need a little bit time to do it. Because we have such system of homomorphism, so it means what? That I have big model, that I have 2, then I have 2, then again I have 2, and so on. Yes, and the homomorphism exists in a case when something here is subrepresentation. Yes, and now let me recall that in a case of SL2 hat, such kind of structure we usually use to write down the resolution for trivial representation in this case, using Fermat representation. So, and so how it is going on. So this is trivial representation. Then we have map from Fermat with highest weight 0 to this. Then we have two Fermat which generate by these two vectors. Let us denote them by V1 plus V minus 1. And we have these two more. Then we have maps from V2 plus V minus 2. Then we have V3 plus V minus 3 plus so on. Yes, and then, no, and what is this? It is usual Rubinstein-Gelfand resolution of trivial representation for SL2 hat. And correspondence gives us correspondence, it means that we can cook up from screening such kind of homomorphism in my category, and they composed by the same way. And so it gives us some complex, which is following. It is F0, which is going on to F1 plus F minus 1, then it is going on plus F2 plus F minus 2, then it is going on like this, and their corresponding weights are yes, I think that, no, it is complex. Yes, and differential are simple here, that it is just to this one. And differentials here more complicated, that you see that, no, it is like here. It is, if we have map from this to this, it is 2 by 2 matrix. And this 2 by 2 matrix, here all elements are matrix, are some expression in terms of E. And here they are expression in terms of this screening operators, and such expressions are basically the same. Yes, and then we can calculate this complex, and first of all, what is this? That maybe I mentioned that if we have one screening, then with one screening we have corresponding map. This is Fock space, this is Fock space, and kernel of this map is a vacuum representation for Virasoro algebra. But and so one way to think it, that if we consider two Fock space and map between them, then this object can be understood. No, it is complex of something, but in some sense, in some DG category and something like this, it is vacuum representation of Virasoro. And actually, Virasoro itself, vacuum representation of this, it is just a kernel of this map. And if you consider this complex, it pretends to be some substitution of vacuum representation of vertex operator algebra corresponding with SL2 hat root system. But the point is that it cannot be vertex operator algebra, surely, because this complex, we expect to have vacuum representation here. But this complex has not homology in this place at all, only one. Therefore, we have complex. In principle, we can play with this complex as something like vertex operator algebra, but it is not. It is some complex of Fock spaces. About homology, I explain in a moment what they are. But one important point that we can take this complex, understand it as a vacuum representation, and try to make up all standard business, representation, and so on. It is only partly possible, but it is very, very old standing and good question how to do it. Now something about this question, about this complex. And how to study it. And also what I want to say that also if no there idea of local integral of motion and things like that are following. That in this complex we have the action of some operator, which is d over dz, which commute with differential. And after factorization of this complex, some homology appear here. And these homology are in correspondence with local integral of motions, which I explained yesterday. But first, the important question is how to study this complex. And here it is some idea that we have Fock spaces like this, and we have vertex operators. And I could not say many things about vertex operators, but and in particular I did not write formula for them. But vertex operator, which is acting from this to this, so it was what? Fi Hj is alpha square Fi plus g. And if you want to write what is this, it is easy. And you have to Fz, suppose it is it is the sum of Fi z minus I, and you have to write that Fz is the exponent sum of hi over I times z minus I, and we have to put parameter alpha here, and have to put two dots here. And it is what? It means that you have write down exponent sum alpha h alpha over hi over I z minus I. First, I is positive, and then you write down the same exponent, and I is negative. And also some shift from this to this you have to put here. And this is the formula for vertex operator, and so well. And if you want to construct this complex, that you need to know something about this or that way. You need to know either about what I said about category, or usually people compare these things using description in terms of homology of local system, and they just calculate the errors in this complex. But it is what we, with Edith Frankel, call classical limit. It is possible to see with this what is going on if parameter alpha goes to 0. Yes, and in this case, situation become easy and controllable. And if you look to this expression, then and if alpha go to 0, surely you have to be careful. And if alpha go to 0, that surely this will be 1 and this will be also 1, and so it will be nothing. But you have to make up a little bit more subtle calculation and look first term in this expression. And a result of this expression, of this calculation, will be following. That first of all, what is this Fock space? Fock space is the polynomial in creation operators in h minus 1, h minus 2, h minus 3, and so on. Then you take these screening operators, and which is acting from this to this. But for alpha equals 0, then on this space in a Fock, this part is acting like creation operator, and if h1, h2, h3 are acting like annihilation operator, and they are derivatives. That h1 and hi is d over dh I minus I, but with I here. Yes, and if you make up this calculation, then in the limit you get also operators, but now alpha is 0, so it means that this operator is acting by this way. No, because it take vector from this and send it to here, to this. If alpha is 0, this will be this, because they're all collapsing in one space. Therefore, you see, and these limiting things, it will be the limit of this, and it from this point of view, our operator will be the following. This is sum d over dhi. This, it is I is negative, and here is some polynomial pi I. Yes, and I want this expression have degree -1. So first term, it will be d over dh minus 1 plus d over h minus 2, here polynomial of degree 1, grading 1, and so on. And the expression which you get here, it is, you can get from this. So they look like slightly like Schur polynomials, but not precisely. But expression rather close to this, and you can easily see it from this. It will more or less expansion of this in Z, but you have to send alpha to 0, so it means alpha dependence disappear. So it is rather simple things, and so result of this give you vector field. And so again, what I claim, that surviving things will be vector fields, and it is acting by annihilation operator of this. And first of all, mysterious things about the third relation in such limit is some precise statement. So you get two vector fields, maybe x plus and x minus, acting in polynomial rings and h minus 1, h minus 2, and h minus 3, and these two vector fields satisfy third relation for usual SL2, and in hat it is x plus, x plus, x plus, x minus is 0. It is this, yes, and with x minus also. Now, no, first of all, it is interesting what really we get. And also what is happening with complex. But with complex it is not big deal, because it means that we have some space. In this case it is just F0, where this nilpotent algebra is acting. And we just calculate if we want to calculate the cohomology of this algebra with such coefficients, then if we want to do it, we write down precisely the same complex. No, because if we calculate the homology of nilpotent algebra, then you can do what? You have to take resolution of trivial representation, which for us will be this plus this plus so on, and take home from this to F0, and it gives you just the limit of our complex when alpha goes to 0. Yes, this is precisely this story, and it is nice that it is possible to see by this way. But one more thing, that if you have two vector fields, maybe x plus and x minus, acting in a vector space with coordinate h minus 1, h minus 2, and so on, it means that we have action of the algebra or nilpotent group somewhere. And the question is where the algebra, nilpotent algebra, can act. No, surely if you have nilpotent algebra in SL2 hat, it surely can act on itself by vector fields, and it also can act on quotient. And in this case, the result is following, that what is nilpotent algebra for SL2 hat? It is the following. We have operators E0 and E1, Then we have a bracket. This is a bracket of E0 and E1. Then I can take bracket here. I can take bracket here. Yes, and third relation is saying that I have one bracket, two brackets, three bracket is 0. But after that, I can continue this procedure like this. Then like this, it is this. Yes, and then what is this? And so it is E0 and this is E1. But nilpotent algebra is what? Nilpotent algebra, we have SL2, then we have T SL2, then we have T square SL2. Who is who? This is E0 and this is E1. Yes, and in this picture, this is E0, this 3 is this SL2, this 3 is this SL2, and so on. Yes, and inside this nilpotent algebra, we have so-called principal commutative subalgebra, which is what? Which is E0 plus E1. It is two elements here, then sum of these two elements, sum of these two elements, and so on. And this is what people who are working in Katz-Moody algebra using for constructing. So if you have fundamental representation, you have two different Bosonizations. One of them initial Lipovsky-Wilson, this is such Bosonization maybe, and not Katz-Frenkel, but for SL2, usual Bosonization was invented by some other people. Though anyway, Katz-Frenkel invented the generalization to higher rank. Yes, but anyway, it is such kind of commutative algebra, which is just sum of these two, sum of these two, and sum of these two, which is calling, let us denote corresponding algebra as a tilde, and and statement is following. That we can take nilpotent algebra and take a quotient of this by a head, by this abelian subalgebra. And so we take the quotient from the left, but the action from the right maybe. But left action remaining, and the fact is that what we get by this way in a limit, when alpha goes to 0, as homogeneous space for nilpotent algebra is just this quotient. Yes, and yes, and because this is a quotient, then what is going on? So if we have nilpotent group itself, and we have function on nilpotent group, and if we have left action, and I calculate, no, it is always our algebra. If I calculate some cohomology, that this representation is projective, and so on, we have homology only in degree 0. But if I take a quotient by some subalgebra, then, and taking like this, then the result of this coincides with cohomology of this subalgebra. And in this case, this, as I said, this algebra is abelian and therefore corresponding, and it has generators in degree 1, 3, 5, and so on. Therefore, the cohomology of what we calculated expected to be, no, in this case it is just it. This is algebra. No, because it is a cohomology of abelian algebra, it is exterior algebra with generator 1, 2, 3, 5, and so on. Yes, and so this is a result in a classical, in such a classical limit, but in no, the point is that if you look to this complex, then it is possible to show after some work that when if alpha is not 0, so if we move from the limit infinity to finite alpha, that the homology does not change. Then no, this is easy. But for example, what many years ago we did not do with Eric Frankel, that, well, if you are talking about the homology in this situation, that it is standard fact, and then we have such kind of homology, and we have not only homology, but we have this operator of product, which give us this structure of Grassmannian algebra with generators in degree 1, 3, 5, and so on. And if we, instead of this, consider this as a complex, and if you take its homology, then what? No, the statement about homology is following, that in F0 only one is survive and all other things are not in the kernel. If you have here quotient of the kernel up to the image, then you have, you see how it is going on. So here top vector here, then we have one vector here, then we have two vectors here. Here actually we have two top vectors, and then it is something is going on. So we will have one, and here it is starting lower. So one homology class will be here. It is from this grading on level 1. Next one on level 3, next one on level 5, and so on. And so homology calculation just saying us that here we have such grading, and in odd level we can see one homology class only. So this is the result of such calculation. But then, in principle, we want to work with this as with the vertex operator algebra. So what does it mean? No, but surely we can. These things are representation of Heisenberg, and we have to manage to do the following. We have to put such a complex in 3 points on a line and trying to calculate something like correlator. And to see that this correlator recover us, if we do it in correct way, this product in this Grassmannian algebra. And no doubt that it is correct, but I think nobody did it, and so From this point, this is the open question. Yes, it is one thing. And other things that one no, I have a few minutes, but I want to stop. But about this, I want to say one more thing. That no, classically we also see some nice things that. Yes, and by the way, in more complicated situation, maybe what you are doing, that we have what? We have the same story, but more screenings. And some of them are Wikimoto. No, what is going on? Here we have screening for Virasora, and some extra screenings here. And then they collapsing, and if alpha goes to 0, to some vector fields acting somewhere. And suppose we are talking about more complicated W-algebras. Now, if what without big problem with the ADIC we did, but it is only what is corresponding to principal nilpotent. In this case, it is fine, these screenings corresponding to usual W-algebra. This is additional screening. And after that, here they give us, in a limit, the action of something, and this is also nilpotent, but not for SL2. And so it's okay. And if you want to go further, then it depends. But if you here have not Fock space, but SL2 hat representation, for example, and here we have Wikimoto screening, and here we have, in a sense, dual one. In this case, it is also possible. And the difference will be that this nilpotent algebra, this abelian algebra replaced by the usual one, more or less. Yes. If you want to do something more general, maybe you can. Yes. But a few words about the integral of motions. At least if we have nilpotent group, and nilpotent group, and we can understand the nilpotent group as a part of a flag manifold. Yes, and so if it is a part of a flag manifold, it means what? It means that on n we have the no, who is acting actually here? That no, because this n is a part of this, so on F is acting full, in our case, full SL2 hat. And if you consider this n as here as the biggest possible Schubert cell, then on this n we have action of maybe Lie algebra from the right and the action of G hat from the left. Yes, and then what we are doing, that here we identify our things with following, that on this n we have this action of algebra A, what this abelian algebra. Yes, which and this abelian algebra is a part of this, and I have to factorize by this. But this is algebra here. It is some algebra which has generators in degree 1, 3, -1, -3, and so on. And I factorize, say, by this. But because we have action of all, and all this object is commutative, then this part is commuting with this. So the action of this part after the quotient, it remaining, it preserved. So therefore, such kind of operators are acting on the quotient, and because the left action commute with right action, that they commute with this n, and so it means that they're acting on a complex. And in particular, they're acting on cohomology. It is not, it is acting on a complex. So it means that we are, in a classical case, we expect to have here some symmetries which have to commute with all differentials in this complex. And no, surely we can see it from there on the classical limit distinctly, because this geometry of a Fleck manifold immediately says us that it is true. But from the point of view of this, the problem is to find out here some operators which are acting. Now, if we want to see it after deformation for finite alpha, what we want to say? We want to find out some operators which are acting here, which commute with differential. First of all, they commute with this and this. And they are local integral of motions. Yes, and no, last things which I want to say that logically what is going on in after deformation has to be as simple as I explained here in a limit. But technically, definitely not. So in quantum group case, we are doing something very, very, very similar, but by 1,000 times more complicated way. And so real proof of existence of this local integral of motion is huge. And it is yes, so maybe I stop now.
Can we see from today's lecture some non-local KdV Hamiltonian or something like that?
No. No, in principle, yes, but I didn't say enough for that. So better to say not.